Imagine stepping into a massive warehouse where hundreds of IoT devices need to share data seamlessly. If you try Wi-Fi, the network quickly becomes congested and energy consumption skyrockets. Classic Bluetooth doesn't help much either. It drains batteries too fast. That's exactly the challenge Bluetooth Low Energy, or BLE, was designed to solve. BLE allows devices to exchange small amounts of data quickly, reliably, and at very low power, making it ideal for sensors, beacons, wearables, and proximity-aware devices. In this lesson, we'll explore the fundamental building blocks of BLE, the GATT structure, services, and characteristics, and how these enable structured, energy-efficient communication. You'll also learn about the BLE software stacks available on the ESP32, BlueDroid and Nimble, and how to configure your device as both a beacon that advertises data and a scanner that collects it. By the end, you'll be able to design and deploy low-power BLE networks that scale effectively while extending device battery life. At the heart of BLE communication is the Generic Attribute Profile, or GATT. Think of it as a structured library that organizes how devices share information. At the top is a profile, which defines the complete feature set of a device. For example, a heart rate monitor device follows the standardized heart rate profile. Inside a profile, you'll find services, which are logical containers for related functions. Each service is identified by unique UUID. For example, the battery service groups everything related to power status. Within each service, we have characteristics, the smallest building blocks of data exchange. A characteristic might represent battery level is equal to 78%. Each characteristic has a value, optional descriptors for metadata such as units or ranges, and properties that control access, read, write, notify, or indicate. This GATT hierarchy ensures BLE data exchange is predictable, lightweight, and efficient. By organizing information into profiles, services, and characteristics, BLE minimizes packet size and maximizes energy efficiency. In any BLE network, devices take on one of two main roles, peripheral or central. A peripheral is usually a small, battery-powered device that advertises its presence and exposes one or more services. Think of a temperature beacon or a fitness tracker. It's constantly broadcasting small packets of information. A central, on the other hand, is a more capable device that scans for peripherals, establishes connections, and interacts with their services and characteristics. Smartphones, gateways, or another ESP32 acting as a hub are good examples of centrals. Within this interaction, services act as logical groupings, and characteristics are the actual data points being shared, whether it's a sensor reading or a configuration parameter. To keep communication efficient, BLE provides notify and indicate features, which allow peripherals to push updates in real time without constant polling. This design drastically reduces energy use while ensuring devices respond quickly, making BLE perfect for scalable, low-power IoT systems. The ESP32 offers two different BLE software stacks, each with unique strengths. The first is BlueDroid, which is the default stack in Arduino and ESP-IDF. It is stable, well-tested, and provides full support for most BLE features, making it the go-to choice for beginners and quick prototyping. However, BlueDroid consumes more memory and is less optimized for handling multiple simultaneous connections. For more advanced projects, Espressif also provides Nimble, a lightweight, memory-efficient alternative. Nimble has a smaller footprint, leaving more resources for your application code, and is better suited for scenarios where the ESP32 needs to manage many devices at once. For example, if you're building a network aggregator that listens to dozens of BLE beacons, Nimble will perform more efficiently. Choosing the right stack depends on your goals. BlueDroid is great for learning and small-scale projects, while Nimble shines in production environments and large IoT networks where scalability and efficiency matter. Let's look at how the ESP32 can be configured as a BLE beacon. The first step is to create a BLE service, which defines the type of data your device will expose. Next, you define one or more characteristics, such as a temperature reading. For each characteristic, you specify properties. For example, notify, so that updates can be pushed to connected devices automatically. Once your service and characteristics are defined, you start advertising. This makes the ESP32 discoverable to any BLE scanner nearby. In practice, your code periodically updates the characteristic value, say, a new temperature reading every few seconds, and notify subscribers. On the serial monitor, you'll see confirmation of advertising, while BLE scanner apps on a phone or PC detect the device and display its UUIDs and characteristics. This setup closely mirrors how real-world IoT sensors work: lightweight, battery-friendly, and able to broadcast data efficiently to any central device that wants to read it. The ESP32 can also act as a BLE scanner, discovering nearby devices and reading their advertised data. When configured as a scanner, the ESP32 initializes BLE, sets scanning parameters such as interval and window size, and handles device discovery using callbacks. Each time a peripheral is found, the callback provides details like the device name, MAC address, RSSI, signal strength, and any advertised services. You can even filter by specific UUIDs to focus on the devices that matter for your application, such as beacons broadcasting temperature or humidity data. The serial monitor logs this information, giving you real-time visibility into the BLE environment around your ESP32. By adjusting scan intervals and whether to use passive or active scanning, you can fine-tune the balance between detection speed and power efficiency. This setup is particularly useful for IoT projects that aggregate sensor data from multiple devices or trigger actions when a beacon enters or leaves range. When working with BLE, several common pitfalls can derail projects if you're not careful. One issue is UUID conflicts. If two devices share the same UUID unintentionally, connection errors may occur. Another mistake is relying on frequent polling instead of using notify. Polling wastes energy and reduces responsiveness, while notify allows peripherals to push data only when necessary. Running both advertising and scanning simultaneously on a single ESP32 can also drain batteries quickly, so it's better to design proper duty cycles. Keep in mind that BLE packets are small, typically limited to 20 bytes per characteristic per transaction unless you extend the MTU. So always send only the essential data. For troubleshooting, tools like NRF Connect or Light Blue are invaluable. They let you scan for devices, inspect services and characteristics, and test read or write operations. By following these best practices, you'll build BLE systems that are robust, efficient, and ready for real-world IoT deployments. Once you understand the basics, the best way to strengthen your BLE knowledge is through hands-on projects. One great exercise is creating a network of multiple BLE beacons, each broadcasting sensor data, with a central ESP32 scanning and aggregating the readings. Another project could use proximity-based triggers, where actuators respond when a beacon enters a defined range, for example, unlocking a door or turning on lights when you walk into a room. You can also experiment with creating a multi-service ESP32 device where single ESP32 offers multiple characteristics like temperature, humidity, and battery level, all within structured services. For more advanced experimentation, try combining BLE with ESP now, allowing hybrid communication between devices. Finally, you can build a dashboard that collects data from BLE devices and visualize it in real time on a web interface. These projects reinforce your understanding of services, characteristics, and roles while preparing you for real-world IoT system design. In advanced BLE systems, security becomes a critical factor. BLE supports multiple pairing methods: JustWorks, which is simple but less secure, passkey entry, where users enter a code, and numeric comparison, where both devices confirm the same number. Once devices are paired, bonding and encryption ensure that only trusted devices can reconnect securely and that sensitive data is protected in transit. This is especially important in applications like healthcare wearables or payment devices. Another powerful concept is BLE Mesh, which enables many-to-many communication. Instead of one central connecting to multiple peripherals, devices forward messages to each other using managed flooding. This creates networks that can scale to thousands of nodes. The ESP32 fully supports BLE mesh via ESP-IDF, making it possible to design complex systems like smart lighting, industrial monitoring, and building automation. Understanding security and mesh concepts prepares you to design IoT solutions that are not only energy efficient but also secure and highly scalable. By completing this lesson, you've gained a strong foundation in BLE with the ESP32. You now understand the GATT hierarchy, profiles, services, characteristics, and descriptors, and how each P structures communication. You've seen how devices take on roles as peripherals or centrals, exchanging lightweight data through well-defined properties like read, write, and notify. You also learned about the ESP32's to BLE stacks, Blue Droid, ideal for beginners and prototypes, and Nimble, designed for efficient, large-scale networks. With hands-on examples, you explored how to configure the ESP32 as a beacon to advertise data and as a scanner to detect and log nearby devices. Along the way, you reviewed common pitfalls such as UUID conflicts, payload size limits, and energy inefficiencies, plus best practices for avoiding them. Finally, you saw how BLE security and mesh networking extend BLE's capabilities into advanced applications. With these skills, you're ready to design secure, low-power, and scalable BLE-based IoT systems.